So first of all, let's look at some examples. The chemical reaction occurring between the gas and the oxygen by way of the energy, activation energy that started, is causing a what kind of chemical reaction to take place? Come on, chemistry. Heat giving off exothermic reaction, right? So a very exothermic reaction is causing there to be a large amount of energy around here. And then some of that energy is transferred in the form of, if I just place an object in there, that's heat transfer by contact. In other words, conduction, right? If I place my hand right here, am I touching the flame? No. Do I feel the heat? Yes, in the form of transfer by radiation. There's infrared electromagnetic radiation that's hitting my hand from the reaction. Watch out for fire. Now, if I place my hand way up here, I feel heating by convection, right? And as a matter of fact, it's much hotter up here than it is here. Can I explain that by radiation? No, because the farther away I am from the source, right, I'd expect there to be less radiation. And so up here, I'm much farther away, but yet it's much hotter. Why? Because of the convection. Wait, what?
So, okay.
Okay. Now, a couple of other things we're going to do while we're here. One is, what did you say happens when an object heats up? It expands. And its temperature increases and it expands. Right? What I have here is called a bimetallic strip. It's basically two different metals that have been fused together into one strip. Do you think those two metals might expand at the same rate when their temperatures change the same amount? No. I mean, it would make sense that different metals have different properties, right? And so they might expand at different rates. And you would be exactly right. If I heat this band up, it bends. And as it cools down, it will eventually straighten out, right? Now, there's I think it's brass, but the gold colored one has what kind of coefficient of linear expansion compared to the silvery looking one? Yeah, a larger one, right? It's going to expand. For the same temperature change, it's going to expand more.
A larger what? What was it?
It's called the coefficient of linear expansion. You don't need to know that. Just know they expand at different rates. Now, this is really useful because we know, we're going to dive into later, but you already know, that metals not only conduct heat, but they also conduct electricity. And so, if I had, say, I don't know, like a coffee pot, I could put one of these bimetallic strips in there, and I could place it like this. I could put a contact right here that would allow electricity to flow in the circuit. And when electricity flows through the circuit of a coffee pot, it produces heat, which will do what to my bimetallic strip? It'll heat it up. And what happens after it gets hot enough? It bends away from the contact, and what happens?
No more electricity.
No more electricity. It breaks the circuit, no more electricity, and so what happens to the heating? It stops. And then it waits until what happens to this?
Till it touches.
So that's how.
Until it cools down. It's basically, it's a thermostat. And it's what you put in a coffee pot so that you can have the coffee stay warm without boiling it away, right? Because the coffee pot has to sit there for hours on end. If it heated the whole time, it would reach boiling and, you know, either boil away your coffee or burn your coffee or whatever. If it wasn't on long enough, the coffee would get cold. And so it has a little thermostat like this, a bimetallic strip, that when it heats up, it bends away and breaks the circuit, cools off, reconnects the circuit. And so, boom, boom, boom. Incidentally, it's also, you have flashing Christmas lights. They've got one of these. When the electricity flows, heats it up, bends away, turns it off. On, off, on, off, on, off. That's why if you look closely at your bulbs, there's one special bulb every 30, 50 or whatever lights. And if you look in there, you actually see this little bimetallic strip in there. And that's exactly what it is. It's the blinker. He's going to turn everybody on and off.
Is that how you power it?
Yeah.
So is there no way to turn on the sound?
Now, actually, well, used to. There are other ways now that both coffee pots and now with electrical circuits and we can put chips and everything to do everything digitally. But in terms of analog, old school ways, yes, that's that stuff. Right? Now, speaking of, I have here a sphere and a ring. And the sphere is the size that just barely fits through the ring. Now, any idiot could tell you that if I heat up the ball, what will happen? It won't fit through the ring anymore, right? It expands. But you guys aren't idiots. I want to ask you, what happens if I heat up the ring? Will it fit?
Well, if you heat up the ring,
All right, let's vote. How many say, yeah, wait, no, alphabetical order. How many say, no, it will not fit?
Josh.
All right, anybody say, yes, it will fit?
I'm gonna go out and listen.
Okay, are you just going against the flow, or do you have some justification for saying yes? I'm okay with either one, I just want to know.
Wait, what? Okay. I know it's this.
Well, the ball fit you.
All right, so here we go.
Okay.
Can you see it expanding? No, you can't.
Are you serious?
That was my roller coaster question, right? Have I told you guys that story?
No.
Okay, this would be a good time for that story. I had a student who, bless their hearts, were a compulsive liar. And they said things usually to get attention. And we're talking about centripetal acceleration and the roller coaster. And I was making the point that mass cancels out, right, in the equation. If you need more mass to make the turn, you need greater force because of your mass and your inertia to make the turn, but you also have a greater mass, so you have a greater gravitational force, whatever. And so I was making the point that mass is canceled, and so I said, you guys know how when you go to Six Flags, and right before you get on the shockwave, they have you stand on that scale, and they tell you where to sit on the roller coaster based on how much you weigh. And this particular student was like, oh yeah, I've seen that. I was like, but it was so bad that then later they came up to me and they said, oh, well, no, it was at another theme park where they had that number. Oh, you poor thing. I'm not telling you. All right, Right, so that's red hot, right? So would you say that was heated? Right. Drum roll, ready?
Whoa.
Yes.
Did it not expand?
Good pick, JD.
Did expand.
Both, that's what you get. Is it?
Let's look at it.
Don't tattoo my arm with it.
Brand us, give us a Dr. Secret.
I'm tempted.
Brand the table.
All right, let's look. Here's the ring. It's coming. Give it a second.
All six.
You thought, no, it's not going to, because you saw this thing expanding and that inner hole getting smaller. But look, focus on this section of the ring. I'm going to put it over here. What happens to this line? Gets longer. What happens to this line? Gets longer. So if I extend that to the entire picture, what happens to the inner circle? It gets bigger as the outer circle gets bigger. So both inner and outer circles expand, so the entire hole expands. And so it's actually easier to fit it